Today we're on page 2 of the AP Chemistry Chapter 13 packet, and we're going to be discussing Kc and Kp. These are both equilibrium constants, and Kc stands for concentration and Kp stands for pressure. So there are two different ways to express the equilibrium constant when dealing with gases. You could either work in concentration or you could work in pressure. They're very similar in how they're set up. So let's review Kc. It's concentration, which is just the regular equilibrium constant. So if you take a look at the equilibrium I have on top, NH3 is a product. You would raise that concentration to the second. In the denominator, you would put N2 to the first, and you would put H2 to the third. And then if you wanted to find the value of this, you would simply take the numbers from above. So 0.031 molar was the NH3. Square that, put on the denominator 0.85 for the nitrogen, and then a 0.0031 raised to the third for the H2. And when you do the math for this, you're going to come out to be a 3.8 times 10 to the fourth, which is much, much greater than 1. This double greater than sign means a lot greater than 1. And this tells you that the equilibrium will favor the products. So that's everything we've learned already. But now, let's suppose that we're going to be trying to find what's called the Kp. That has to do with pressure. Well, there's a relationship between Kp and Kc, that the Kp, the equilibrium constant based on pressure, is equal to the Kc, which is the equilibrium constant based on concentration, times RT to the delta N. And this RT is just like Pivnert. The R is 0.0821, and the temperature has to be in Kelvin. So let's talk about what delta N means. Delta N means the change in moles of gas. So change in moles of gas. Gas is the key word here. It has to be the moles of gas. So if you take a look back at the top of the paper where we have our equilibrium, you could see that altogether on the left side, altogether on the left side we have 4 moles of gas. This is going to be 4 moles of gas. And on the right side we have 2 moles of gas. So the change is always the end minus the beginning. So 2 minus 4. 2 minus 4 is negative 2. So when we go down here, we're going to do our delta N is going to be 2 minus 4 for the reaction above, which equals negative 2. So when you set up your equation here, you're going to say Kp equals Kc times RT, quantity to the delta N. So we're looking for the Kp, that's what we don't know. That's equal to Kc, which was 3.8 times 10 to the minus fourth. Then we're going to take this whole quantity of the R of Pivnert is 0.0821, and we're going to multiply by the Kelvin temperature, which was 400. We're going to not square, but raise that whole thing to the negative 2. That was the delta N. And then when you find this, it's going to be 35 as your answer. And this would be the value of Kp. Okay, so I'm going to write down value of Kp. But let's write down the Kp expression. It's very similar to what we did with concentration, except now we're dealing with pressure. So you would write Kp equals the pressure of NH3, the product, squared, because that was its coefficient, divided by the pressure of nitrogen to the first times the pressure of hydrogen cubed. So you could see that this is very similar to the Kc expression, except it's in pressure. So the pressure, the Kp, is equal to the pressure of the products over reactants raised to their coefficients, whereas the Kc is equal to the concentrations of the products over the reactants, each raised to their coefficients. And the relationship is Kp equals Kc times RT to the delta N. Now, I had a student one year, his name was Pat Carroll, PC. So you could remember Pat Carroll is right on. Pat Carroll is right on, and that'll help you remember that Kp equals Kc times RT to the delta N.